It costs over $1 million. Looking closely at its mirror-like surface, you are seeing the single roundest object ever created by human hands. Forged from highly enriched silicon, this object spans exactly 93 millimeters in diameter and weighs precisely 1 kilogram. To understand the scale of its physical perfection, imagine if this object were scaled up to the size of Earth. At that planetary scale, the distance between its highest peaks and its deepest trenches would vary by a mere 14 meters. This flawless physical shape exists for a specific mathematical reason. It allows scientists to accurately count the exact number of atoms inside it, and in doing so, redefine the laws of measurement. For 130 years, the global standard for mass was tied to this physical artifact. Known as the International Prototype of the Kilogram, or Big K, this platinum iridium cylinder was the absolute anchor for the measurement of weight. It was kept under 3 nested glass bell jars, locked in a temperature-controlled subterranean vault in France, heavily guarded and rarely touched. But a physical artifact is at the mercy of its environment. Over decades, the cylinder constantly absorbed microscopic atmospheric hydrocarbons, trapped gases, and traces of mercury. Before scientists could conduct mass comparisons, they had to subject the metal to a rigorous manual cleaning procedure. The friction of cleaning physically stripped away microscopic amounts of the original material. This chart tracks the mass comparisons over the last century. It shows a clear downward trend. Over 100 years, the original prototype inexplicably lost approximately 50 micrograms of mass relative to its official copies. The global scientific community was anchoring an entire system of mathematics to an object that was slowly vanishing. Metrologists required a new standard for mass, one entirely immune to physical decay. Scientists turned to silicon. Under the right conditions, silicon can be grown into a highly ordered single crystal structure, forming a perfectly predictable atomic lattice. But natural silicon poses a significant problem. It contains a random mixture of 3 stable isotopes, which throws off any attempt to calculate an exact uniform mass. To isolate a single isotope, a massive international effort utilized Russian gas centrifuges, originally designed for uranium enrichment. This graph shows the intensity of mass numbers resulting from that process. As you can see by the peak at mass number 28, they successfully isolated the silicon-28 isotope to an enrichment level of 99.9995%. The purified gas was transported to Germany, where it was chemically deposited and slowly grown into a solid, near-perfect crystal rod. This extreme, highly resource-intensive chemical purification was the mandatory first step. Without it, physical shaping could not even begin. From Germany, a rough 20-centimeter cylinder of the pure crystal was shipped to the Australian Centre for Precision Optics for shaping. The fabrication started with a harsh grinding process. Technicians used metal and glass laps coated in alumina abrasives to violently strip away subsurface fractures from the bulk material. Automated machinery alone could not achieve the required tolerances. Final shaping required a master optician to manually guide the sphere in a random, looping motion. This unpredictable human motion was necessary to prevent directional grooving on the crystal surface. Relying on constant remeasurement and a slurry of titanium dioxide, the optician slowly achieved a sub-nanometer finish. To produce a mathematically flawless object required for strict theoretical physics, the global scientific community ultimately relied on the tactile judgment of human hands. To verify the exact dimensions of the polished crystal, scientists placed it inside a temperature-controlled vacuum chamber within a custom-built machine called a Fizeau interferometer. They could not rely on a single diameter measurement. Instead, they mapped the complete 3-dimensional volume by measuring the sphere from hundreds of thousands of different directions. This topographical heat map shows the interferometric measurements. The data proved the sphere deviated from perfect roundness by less than 100 nanometers. Yet they faced a contamination problem. During polishing, it picked up microscopic layers of copper, silicides, and oxide. Scientists used X-ray reflectometry to precisely measure the thickness of these microscopic contaminants. With that data, they could mathematically subtract the weight of the surface layer. Factoring out that contamination was the only way to isolate and reveal the true, unadulterated mass of the pure silicon-28 core. Despite the goal of the project, scientists never actually cracked the million-dollar sphere open to count the atoms inside. Instead, they derived the total count using 3 variables: the pure core mass, the complete volume, and the known spatial distance between atoms in the silicon-28 lattice. Combining these, they calculated exactly 2.15 times 10 to the 25th power atoms locked inside the sphere. This precise atom counting achievement, operating in tandem with independent Kibble balance experiments, provided the mathematical certainty needed to formally redefine the kilogram in 2019. The unit of mass is no longer tied to an unstable, degrading metal artifact hidden away in a subterranean French vault. It is permanently anchored to the fixed numerical value of the Planck constant. Today, these silicon spheres continue to serve metrologists as the physical bridge, translating the abstract mathematics of quantum physics into the tangible reality of weight.